Hi guys, in this video we are going to study about the effect of dilution on conductance, measurement of conductance by Wheatstone Bridge method, a strong electrolyte and the weak electrolyte. Firstly, we will see about the effect of dilution on the conductance. Equivalent conductance and the molar conductance both increase with dilution and reaches to the maximum value at infinite dilution. Increasing the temperature reduces the resistance, thereby increasing the conductance. Hence, equivalent conductance and molar conductance increases with increasing the temperature. Here in this case, as we increase the dilution of the electrolytic solution, then there is the dissociation of ion takes place, means the number of ions are increases as well as the speed of the ion is increases on increasing the dilution, and therefore here in this case, that is whatever may be the equivalent conductance and molar conductance, both are increases on increasing the dilution as well as the increasing the temperature. In case of a specific conductance decreases with increasing the dilution, because increasing of dilution, the number of ions present per centimeter cube of the electrolyte decreases. Guys, we know that the specific conductance depends upon the volume of the electrolytic solution. That is, conductance of 1 centimeter cube of the solution of electrolyte is called as the specific conductance. Means when we dilute the electrolyte solution, then at that time the number of ions per unit volume it is to be decreases, and therefore that is a specific conductance decreases on dilution. See the variation of specific and equivalent conductance with dilution. Why a specific conductance and the equivalent conductance are having the variables in case of an dilution? As we know, the specific conductance depends upon the number of ions per unit volume of solution. On increasing the dilution or decreasing the concentration, the number of ions per unit volume decreases, so that the specific conductance of electrolytic solution goes on decreasing with dilution. Means the number of ions per unit volume decreases in case of a specific conductance, and therefore we know that the conductance depends upon the number of ions and the speed of ions. On dilution, as the number of ions increases, but the number of ions per unit volume decreases on increasing the dilution, and due to that one we know the specific conductance depends upon the number of ion per unit volume, and therefore here in this case on dilution the number of ions per unit volume decreases, and therefore the specific conductance decreases on dilution. Okay, this is due to the in case of two cases. What happens in case of weak electrolytes? Means the electrolyte which is to be slightly dissociated or which is not completely dissociated into the solvent, it is called as the weak electrolytes. Okay, here in this case on dilution, the degree of ionization of electrolyte increases, but the number of ions per unit volume of the solution decreases on dilution because of increasing the distances between the ions, so that the specific conductance decreases. Means similar is the case that when on dilution, that is the number of ions per unit volume it decreases, and therefore the specific conductance decreases on dilution. Similarly, in case of strong electrolytes, the number of ions per unit volume goes on decreasing on dilution. Therefore, the specific conductance of electrolytes as well as the weak electrolyte, that is strong electrolyte, decreases on increasing the dilution or decreasing the concentration. means that is the specific conductance for both strong as well as weak electrolyte. It is decreases on increasing the dilution because the concentration per unit volume it is to be decreases, and therefore the specific conductance it is to be decreases on increasing the dilution, and it is to be increases with increasing the concentration of electrolytic solution. See, for the equivalent conductance. The equivalent conductance of an electrolytic solution depends upon the number of ions and the mobility of ions. That is what we call the speed of ions. Then on dilution, the interionic forces or attraction between the oppositely charged ions decreases on dilution, and therefore the ions are free to move from one point to the another point, or it is free to move in an electrolytic solution. And due to that one, that is a equivalent conductance, it is increases on dilution. In case of an weak electrolytes, a degree of ionization is increases on dilution and interionic forces decreases on dilution, so that the number of ions and the speed of ions both increases, which results in the increasing the equivalent conductance. Similarly, in case of a strong electrolyte, and we know that the strong electrolyte is already has the 100% degree of ionization. Okay, means that is whatever may be the molecules of the electrolyte are dissolved in any solvent, at that time it is to be 100% dissociated, and therefore it has a 100% degree of dissociation, and therefore the dilution could not affect on the number of increase in the what we call the degree of dissociation of the or degree of ionization of the electrolytic solution. But in this case, the increase in the equivalent conductance is not due to the increasing the number of ions, but mainly it is due to an increase in the speed of ions with dilution. As dilution is increased, the interionic forces between the oppositely charged ions it is to be decreased, and as a result the speed of the ion increases. This is the graphical representation of variation of the equivalent conductance with the dilution for strong as well as the weak electrolyte. See here, in case of a strong electrolyte, as the concentration is increased, the equivalent conductance, okay, means as on dilution, as dilution it is to be decreases, the equivalent conductance, sorry, dilution is increases, equivalent conductance it is to be increase, or what we call as the concentration increases. In this case, equivalent conductance is also that is decreases. Okay, means equivalent conductance it is to be increases with the increasing the a dilution due to the mobility of ions. Similarly, for weak electrolyte, on dilution the dissociation or the degree of ionization it is to be increases for weak electrolyte, and therefore there is a sudden decrease in the equivalent conductance takes place in case of an weak electrolytes. This is about the molar conductance, that is how there is a variation of molar conductance with the dilution. Similarly, that equivalent conductance, that is in case of a strong electrolyte, suppose we have taken the potassium chloride, there is a gradual decrease in the increase in the molar conductance, or decrease in the molar conductance takes place with increasing the dilution. And similarly, that is the molar conductance it is also be that is the decreases with the dilution. Then see here, measurement of conductance by the Wheatstone Bridge method. This we know the conductance is nothing but the reciprocal of the resistance, and This resistance is measured using the Wheatstone Bridge method. That is the circuit diagram which is to be used to determine the conductance is as shown in the figure. In this principle, it consists of the four arms, containing the resistance R1, R2, R3 and R4. R3 is the variable resistance and R2 is the unknown resistance. When null point is obtained, that is, there is no deflection in the galvanometer, then at that time there is a relation that R1 divided by R2 it is equal to R3 divided by R4. Knowing the values of R1, R3, R4, we can calculate the R2. In finding the resistance of the solution of electrolyte, a special type of cell has to be used, such as the solution is present between the two electrodes. The cell thus used is called as the conductivity cell, and it is made up of from the Pyrex glass and has two platinum electrodes at a fixed distance apart. That is, we see here in this figure, it has this type of a conductivity cell. It has these two electrodes. So two electrodes, that is that two electrodes are to be present in a conductivity cell, or it is to be dipped in an electrolytic solution. And whatever may be that conductivity cell here in this case, it is made up of this Pyrex glass. During the measurement of the resistance, a certain serious problems occurs in case of Wheatstone Bridge method. That is, in case of this Wheatstone Bridge method, if we use the direct current, it causes the electrolysis of the solution, and it results in the concentration of electrolytes near the electrodes changes, and this results in the change in the resistance of the solution, and this effect is called as the polarization. Means when we use the DC current, the electrolysis of the electrolytic solution is to be takes place, and the concentration near the electrode it is to be changes. As the concentration near the electrode it is to be changes, it results in the what? Change in the what? Resistance of the solution. Resistance of solution gets changed, and this effect is called as the polarization. Means when we use the DC current, a polarization it is to be occurs near the electrode on in electrolytic solution. To overcome this problem, that is the DC current it is to be replaced by the AC current of frequency 500 to 2000 cycles per second. And when we use the AC current, the galvanometer does not show the null point, and due to that one, that is the galvanometer it is to be replaced by the hot earphone, and the electrodes are coated with the finely divided platinum black. And when we move the jockey from the point A to point C along the wire AC, then at that point D, this earphone shows the low sound, and D point is the null point, and at this point, that is the resistance R, it is nothing but the resistance of wire AD, and resistance X that we have to determine, that is equal to the resistance of wire AD divided by the resistance of wire CD. And the resistance of wire AD, it is approximately, or it is equal to the length of wire AD, and resistance of wire CD, it is the length of CD. The resistance X, it is equal to, the above equation is modified as the resistance X is equal to the resistance R into the length CD divided by length AD. And therefore, we know that the conductance is nothing but the reciprocal of resistance. That is, X is the resistance that we have to determine, from which we have to calculate the conductance, or we have to measure the conductance. And therefore, the conductance C, it is equal to 1 upon X, and that is equal to 1 upon R, that is the resistance, into the length AD divided by length CD. Means above equation is modified as the conductance C is equal to, that is nothing but the reciprocal of the resistance that we have to calculated, unknown resistance, that is equal to the 1 upon R. R is nothing but the what? A resistance which we have to fix in the resistance box. It is into the length AD divided by length CD. And therefore, that is the specific conductivity kappa is related to the conductance C as already stated equation, that is a specific conductance kappa, it is equal to C into L upon A. L is nothing but the what? Length of the distance between the two electrodes, that is the L, and A is nothing but the area of cross section. And therefore, L upon A for all the conductivity cell, it is constant, that is, as L is equal to 1 centimeter and A is the what? 1 centimeter square. And at that time, that is L upon A, it is a constant, and that is called as the what? Cell constant. The relationship or the ratio of distance between the two electrodes and the area of cross section of the electrode is known as the cell constant. As the distance is 1 centimeter, area of cross section is 1 centimeter square, then at that time, that is, it is the ratio of that L upon A, means 1 centimeter upon 1 centimeter square. This is the constant, and therefore it is called as the cell constant. And therefore, the specific conductance is equal to this conductance into the cell constant. Guys, you have to remember this equation which give the relationship between the specific conductance and the conductance in the form of the cell constant. Then we'll see about the strong and weak electrolytes. See here, we know that the pure water does not conduct the electricity because it does not have any soluble salts, or it does not have any type of an electrolyte to conduct the electricity. See here, when we add the electrolyte to the pure water, then at that time, what happens? The electricity, it is to be conducted throughout the electrolytic solution, and the electrolyte produces the ions in the water and it conducts the electricity. Then see, what is the strong electrolyte, what is the weak electrolyte, and non-electrolytes. The strong electrolytes are fully dissociated in the water, means the degree of dissociation or degree of ionization of strong electrolyte has more value. In case of a weak electrolytes, it is incompletely dissociated in water. As example, acetic acid in water and ammonia in water, and therefore they are incomplete dissociated in water. They have the less value of degree of ionization, and therefore such type of substances are called as the weak electrolytes. And non-electrolytes could not be dissociated in water, and they do not dissociated in water, and therefore that type of an electrolytes or they are non-electrolytes. Example is when sugar, alcohol and oil is dissolved in water, they do not dissociate and they do not conduct the electricity, and therefore such substances are called as non-electrolytes. See here, the strong electrolytes conducts more electricity and the weak electrolytes conducts a less electricity. Then see the examples of strong electrolytes and weak electrolytes. Strong electrolytes such as hydrogen bromide, hydrogen iodide, then hydrogen chloride, sulfuric acid, nitric acid. These are the strong acids and they are completely dissociated in aqueous solution, and therefore these are the examples of strong electrolytes. Strong bases like lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide and cesium hydroxides. Soluble salt like NaCl, magnesium sulfate, potassium dichromate, ammonium nitrates are the examples of soluble salts of strong electrolytes. Then what are the examples of weak electrolytes? Weak acids such as acetic acid, that is carbonic acid. Weak bases like ammonium hydroxide, sodium carbonate. Insoluble salt such as silver chloride, lead sulfate and calcium carbonates. Okay, these are the examples of the strong and weak electrolytes. Thank you guys. If you like this video, please like and subscribe to listen or to show the more videos about the electrochemistry. Thank you.